All right, we have one more lesson for this chapter, and this lesson is going to be the second half of the last two sections from this chapter. So we're going to do the second half of section 6.4 and the second half of section 6.5. These are two different applications of differential equations, and really it's the only application that we have this entire chapter. So that being said, you are going to have to know how to solve these equations for today. So maybe pause and you come back, and remembering that to un-ln we exponentiate with a base of e, to un-e we ln, and to other exponents we ln, and then we're going to end up having to divide. If you need some help on these, come to office hours. I can help you out with those. That was homework from last night. And here we go with exponential growth and decay. Exponential growth is really when you talk about a population growing at a rate proportional to its population size. So we actually have up here an example with rabbits. And the way that we can think about this is the number of rabbits in a population increases at a rate that is proportional to the number of rabbits present, at least for a while. Okay, I know I'm just reading exactly what's on the board, but let's say we have, we start with 2 rabbits, right? And those 2 rabbits, without getting too graphic, they reproduce, and they produce more rabbits. And then those more rabbits reproduce again, and they produce more rabbits. And then as the population gets bigger and bigger, you're going to produce more offspring for each generation. So that's what we're talking about when we say a population increases at a rate proportional to its population size. And actually, when we talk about these rabbits, I actually had to pause the video because I wanted to go Google it. You can Google this. There is a rabbit in the, or not a rabbit, there's an island in somewhere in the Sea of Japan, and I'm gonna butcher this name. It's Okunoshima, and somebody in their infinite wisdom decided to introduce rabbits to this island, and those rabbits started reproducing. They weren't indigenous to the island, but they started reproducing, and pretty soon this island became overrun with rabbits. It actually has the nickname of Rabbit Island. So look it up. You can actually see videos of people. The first video I see is guy gets smothered by bunnies on Japan's Rabbit Island, exclamation point. So you can see people getting attacked by bunnies. So that is an example of exponential growth. Most populations of living creatures will model this growth for a while. So something that does happen, you start to run into limitations for that population, like they start to run out of resources, they start to starve, they start to cannibalize, and you stop modeling that exponential growth. But we do model exponential growth for a little while. Any population of living creatures follows that. Other things that increase or decrease at a rate proportional to amount present include radioactive material and money in an interest-bearing account. And actually, something that I saw on the news, they were mentioning it, I believe, just this morning. They were talking about the rise in COVID cases, and they were saying that with the increase in the rate at which these the people are catching COVID, it's modeling this exponential growth, because you have the more people who have it, the more people they give it to. So again, we're talking about the rate of growth being proportional to the size of the population. And the way that we put that mathematically, we use this differential equation. dy dt is equal to ky, where y is the population and t is a unit of time for whatever the population that's growing is. Now, what you see here, proportional to the population, means you have some sort of growth factor that you multiply the population by, and you can get the growth rate at any particular moment, at any particular population size. Moving forward, to give you the general solution for an exponential growth problem, what we do, we use that strategy that we had from yesterday of separation of variables. So I can get my dt over to the other side by multiplying by dt, and get my y to the left by dividing by y. So all of a sudden, I'm left with my separated differential equation of dy over y is equal to k dt. Now keep in mind, k is just a number, so I do technically have my variables separated. All my y's on the left, all my t's on the right. I can now integrate on both sides to find my, not my general solution yet, but on the way to my general solution. So here on the left-hand side, y has an exponent of -1 since the linear factor is in the denominator. This left-hand side becomes ln. Technically, it would be the absolute value of y, but keep in mind, y is talking about a population. This is a real-world application of this. No population is ever going to be negative. We're talking about like number of bunnies. If you can show me what -2 bunnies looks like, I'm not going to offer anything because you can't. -2 bunnies does not exist. So we're just assuming that the population is positive, and it's a pretty solid assumption here. Is equal to, remember k is just a constant multiple, so we have k integrated with respect to t. That's just going to become kt and plus c. So we have ln of y is equal to kt plus c. Now we can produce an initial condition to figure out what c is. That initial condition is just, in general, if t is equal to 0, we call the population y naught. Because why not? That was a joke. No, naught is just another way of saying 0. So y sub 0 you read as y naught. And y naught just means the population at time t equals 0. So looking up here, plugging in my initial condition over here, I now have ln instead of y. I sub that with y naught is equal to k times, instead of t, I've subbed it with 0 plus c, and I can see that the t equals 0 makes this easy to solve. It's just ln of y naught is equal to c. Now I go back and I plug that into this equation, and I now have ln of y is equal to kt plus ln of y naught. Going another step here, I need to solve for y. Again, I did reference you to the do now. That would have been your do now if you were in here. In order to un-ln, we need to exponentiate with a base of e. So e to the ln of y is equal to e to the kt plus ln of y naught. And now we try to simplify this. I mean, e to the ln of y, those cancel out. We're left with y is equal to, I can rewrite e to the kt plus ln of y naught as e to the kt, not plus, using my exponential rules, times e to the ln of y naught. So again, that's just like an algebra 2 kind of situation. So now I see e to the ln of y naught, e and ln over here cancel out. I'm left with my general solution of an exponential growth model to be e is equal to y naught, e to the kt. That's your general solution, where y naught, again, is the population when your experiment begins. This is important. Since we did that process once, you never have to repeat that process. You can repeat the process if you forget the general solution, which again is right here. The y equals y naught, e to the kt. Again, we should recognize that that is the general solution to the differential equation dy over dt is equal to ky, and if y equals y naught when t equals 0. And again, that is just saying that y changes at a rate proportional to the amount present. K, sometimes it's called the growth constant, sometimes it's called the decay constant. If your k is greater than 0, your population is going to be getting bigger. That's going to make it a growth constant. If k is less than 0, meaning k is negative, you have a decay constant because your population is getting smaller and smaller and smaller. Some applications of this, again, bunnies reproducing for a certain amount of time until you reach a carrying capacity. Another application is interest in an interest-bearing account. If money is invested in a fixed interest account where the interest is added to the account n times per year, the amount present after t years is a of t is equal to a naught plus, or times quantity of 1 plus r over n to the nt power. In general, we don't refer to the a naught as a naught. We refer to it as p for the principal amount in the account. If the money is added back more frequently, you will make a little more money. The best way to do this, the more times you compound your interest, the higher n, the better your result is going to be. So the best result is if n gets as big as possible. If n gets as big as possible, that means that you have infinite n's. So here, having infinite n's means you're compounding the interest every single instant of every single point in the year. So banks can employ someone to just sit somewhere and constantly calculate the interest rate, right? No, of course they wouldn't do that. That would be, as I put it here, whackadoodle. Instead, we assume that the rate is growing at a rate proportional to the amount in the account. So what we do here is we model it using this differential equation, where the amount in the account is equal to some arbitrary constant times the amount of the account. That's basically the same thing as dy dt is equal to kt, except we're using different numbers. Now, if we call the initial amount a naught, we can use that general solution to get a of t is equal to a naught e to the rt. Now, just like I said before, instead of referring to it as the initial amount, we just call that the principal amount so that we can get this nice formula that you guys learned last year. It's called the PERT formula because the amount is equal to the principal times e to the rt, where r is your rate of your interest rate, and t is your time, and p again is principal. So just to show you a non-calculus-y kind of thing here, suppose you get $500, you deposit $500 in an account which pays 5.3% annual interest. How much will you have 4 years later if the interest is compounded continuously or if it is compounded monthly? So continuously, we have the really easy formula to plug this into, the PERT formula. For part A, our amount in our account is going to be dependent on several different variables. We have our principal amount. Remember, A is equal to P e to the RT. Our principal in this case is going to be $500. So we have 500 e to the R. Our R is our interest rate, 5.3%. Please don't put that in as 5.3. You need to put it in as a decimal, 0.053 times our T. Our T is going to be, let's see, T is measured in years. So times 4. And break out your abacus and start doing it. Just kidding. So we can see here, I've just pulled up my calculator and I'm just going to do that 500 e to the R times T, and we can see $618.07. Okay. Approximately $618.07. So if I was to compound my interest continuously, I'm going to get $618.07. If I'm going to compound monthly, I'm going to go back and copy down my formula of A is equal to the principal times the quantity of 1 plus R over N to the NT power. So again, looking at that, I can see that my principal is 500 times the quantity of 1 plus my R, 0.053 over n. Now, n is the number of times compounded per year. So I can see monthly, that's going to give me 12 to the nt, so 12 times my t, 4 years. So here, to figure out how much money I'ma have in my bank account if I compound my interest monthly. Give me 1 second here. We are going to have 500 times the quantity of 1 plus 0.053 over 12 to the 12 times 4. $617.70. I know some of us are going to want to round up, but keep in mind banks are evil. So this would probably, the bank would give us $617, and they would round that down. Just because, again, banks are evil. They truncate, they don't round. So you can see compounding continuously is better. Is it a lot better? No, because we had a short time period of the money in the bank account. But anytime you can do continuous compounding over compounding n times per year, it's always going to be better. So again, there's an example of an application of exponential growth. An application of exponential decay now? That's a little bit different. Let's look here. Where is my active inspire? There we go. Radioactive decay. Radioactive decay is an example of exponential decay. What we have in this situation is the amount of radioactive material that you're losing is dependent on how much radioactive material is there. This is how we can do things like carbon dating. We can see how much carbon has what's the word? Gone to a different isotope, I think, if I'm remembering my chemistry correctly. I don't remember all the chemistry, I just know how to apply it. So here, we can use the half-life of a certain material to do some aging, to measure the age of something that we're interested in. In order to find the half-life, you use the radioactive decay formula, which we set up as y equals y naught e to the negative kt. Notice we use the negative in the formula right there so that we can make sure that k, our decay constant, is going to be a positive. So it's still the decay constant, but we include the negativity in the formula. The half-life is the amount of time required for half of the material to decay, for you to get half of the material. In order to find the half-life formula, and I know some of you that have taken chemistry know the half-life formula, but what you look at here, y naught is the initial size of the population, so that would mean half the initial population is going to be equal to half y naught. So in order to find out how long it takes to produce half of the initial population, you take your population and call it half y naught. So half y naught is equal to y naught e to the negative kt. So now to figure out this formula for the half-life, we just need to figure out what t is. So starting off, I can divide by, y naught. So dividing by y naught is going to give me half is equal to e to the negative kt. Now there's a variety of ways that we could proceed with this one. The next thing that I might like to do is take ln on both sides. So I can have ln of 1/2 is equal to ln of e to the negative kt. Now looking at that, I know ln and e cancel each other out, so I'm left with, let's flip the order on here. Negative kt is equal to ln of 1/2. Now looking at that, I don't like the negativity hanging out. So since I don't like that negativity, I'm just going to get rid of it by multiplying by -1. when I multiply by -1, I'm going to get kt is equal to negative ln of 1/2. I'm running out of space, so I'm just going to have to go right up here. So again, we've got kt is equal to negative ln of 1/2. Now I see that negative ln of 1/2. I don't like negatives hanging out in front of ln's, so I'm just going to bring that negative one coefficient up to my exponent in here. So it's going to be ln of 1/2 to the negative first power. Well, 1/2 to the negative first power is just going to be ln of 2. So now my equation is kt is equal to ln of 2. My half-life equation here, in order to figure out how long it's going to take for me to get half of my material, or half of my material to decay, take ln of 2 divided by k. There's your half-life formula. You simply take your decay constant, divide ln of 2 by it, and you can find out how long it's going to take for you to lose half of your material. Again, those of you, I think it comes up in AP Chem. I believe you use the decimal approximation of ln of 2 to divide by k to find out the half-life. The half-life of a radioactive substance with rate constant k, where k is greater than 0, is half-life equals ln of 2 divided by k. Oh, here we go. This is an actual very timely kind of problem here. Exponential growth never really maxes out. So it makes it not really tangible for certain situations. Like your money in your bank account, you can never have enough money. So your money's never going to max out. But when we talk about like those bunnies on an island, eventually the bunnies run out of resources, whether it's they run out of stuff to eat, so they start cannibalizing and eating each other, or they run out of physical space to stay in their area. There's going to be something called a carrying capacity. The carrying capacity is the most number of thingies in the population to fit somewhere. So here's a tangible way to think about it. If I have deer continually reproducing in my backyard and they are locked in my backyard, they can't leave my backyard, what will eventually happen? So I have 1/3 of an acre. This green box is my backyard, all right? So actually I'm not going to start with one deer because that's just kind of, again, not to get blue about it, but it's, if you have one deer, you're going to have one deer forever, right? So if I have 2 deer, right? Those 2 deer are going to get together and they are going to reproduce. And all of a sudden, I have 4 deer in my backyard. And those 4 deer are then going to reproduce. And all of a sudden, I have 8 deer in my backyard. Once I have 8 deer in my backyard, then the population of my deer is going to cause my population to grow faster. So I can see now I have this many deer. And pretty soon, I'm going to have deer on top of deer, on top of deer, on top of deer. I'm going to run out of space. So what actually happens when we're talking about, oopsies, when we're talking about exponential growth, you have this concept of carrying capacity. And we're not talking about what causes those carrying capacities. We're just talking about it happens. So there's some sort of limitation. And we enter something called logistic growth. So logistic growth matches an exponential growth for the first part of the situation, but then it tapers off so that you continually approach what's called our maximal carrying capacity. Some of you have seen this kind of growth before. If you've ever played a game, okay, so here's why this is a timely example. The game of Plague Inc. is where you make up a disease and you try to get that disease to kill the entire planet. At the end of that game, you can actually look at a graph of the growth of your disease, and you can see that it spreads to people and it starts getting faster and faster. But then when you get to a certain rate, it tapers off, and eventually it's going to have a horizontal asymptote at that maximal carrying capacity. Right now, what we have in society, this whole pandemic that's occurring, we are people that are infected are able to communicate that disease to other people very easily, and that's one of the dangers to this. But if you have one person that's sick, he goes out and gets one other person sick. Then those two people go out and each get two more people sick. It becomes like these deer until we get to half of the carrying capacity, which is half of the population is sick with this. This is where you see people talking about things like herd immunity. You want to get up to that halfway point, but you want to keep it kind of slow before you get to that point. Now, I'm getting too into the weeds on this. Let's go into, here we go. Here is the actual differential equation for our logistic growth. This thing right here, where we have dp dt is equal to kp times the quantity of m minus p. In that paragraph right up here, we want the growth rate to approach 0 as p approaches maximal carrying capacity. So m is our maximal carrying capacity, p is our population, and k is our growth rate. All right? So that differential equation is going to be very important. And we're going to flip to page 365 in our books to try to follow along on exploration 2. Now, just to give you guys a heads up on what I have on this page right here, this graph right here is the graph of this equation right here. This equation is the dp dt. So our y axis on this graph right here is the rate of growth. We're going to label that as dp dt. Whereas our independent variable here is our population size. I made up a growth rate and a maximal carrying capacity just to show you what this function looks like. And when we graph it, again, this right over here would be our population. So this is a graph of population versus the rate of population growth. Be careful, the height here is not how big the population is, it is how fast the population is growing. If you want to relate this to the COVID, you can actually call this, as we get bigger and bigger, we have more people getting sick per day. So if you're looking at those indicators on the news every single day, that really shows up. Now here, you can see my window. If you want to reproduce that on your own graph, on your own graphing calculator, feel free to, because we are going to have to refer back to that for this activity. Now, all of the questions that we will answer here are going to help you out. As far as I've seen on the AP test, 9 times out of 10 that a logistic growth problem pops up, you can answer those logistic growth questions with the answers to these questions right here. So consider a positive population that satisfies dp dt is equal to kp times the quantity of m minus p, where k and m are positive constants. For what values of p will the growth rate dp dt be close to 0? Now we can see that on our graph, can't we? We know the growth is going to be close to 0 when that graph is close to the x-axis. So again, looking back over here on this graph, we want the growth rate to be near 0, right? So we want the growth rate to be down near that x-axis. That's the height is our growth rate. We can see a growth rate of 0 over here and a growth rate of 0 over here. Why do we produce 0 growth rates there? Well, here, remember, our x-axis is measured out as our population. over there, our population is going to be nothing. When we have a population of 0, how much are we going to be reproducing? Like we've got one, if we've got no sick people, how many people are going to get sick? Nobody to spread the disease, so nobody else is going to be getting sick. Up here, we have our population is darn near, actually, man, what is that? I can see right up here, my x max is 10, right? And my x scale is 1, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that's odd because that 10 pops up right here. That 10 is my maximal carrying capacity. And the reason why this works out, by the way, again, what I'm looking at here, the answer to number 1 is at p equals 0 and p equals m. I'm again looking for where is my population growth equal to 0. If I look at the differential equation, if I plug in 0 for p, we're answering again number 1. If p equals 0, that means dp dt is equal to k times 0 times m minus 0. It doesn't matter what our maximal carrying capacity is, just by the math, that means that the growth rate has to be equal to 0. Likewise, if I make my p equal to my m, that's going to mean that my dp dt is going to be equal to k, change my p to my m, times the quantity of m minus m. M minus m, that's 0. K times m times 0, that gives me 0. So regardless of what my maximal carrying capacity is, growth rate is going to be equal to 0 at p equals 0 and p equals m. So that's the answer to number 1. One thing that you have to know is the growth rate is nothing when you have no population and when you reach your maximal carrying capacity. As a function of p, the rate of growth is a graph that is an upside down parabola. And we saw that in our graph over here, but we can also see that if we distribute the p, we would get a negative p squared, or negative kp squared. So that's showing us that that should be an upside down parabola because we have a negative x squared value here. So what is the value of p at the vertex of the parabola? So let's look back at our graph right here. We know how parabolae work. If we can find our two intercepts right here, we know that the vertex of the parabola is at exactly halfway between there. So the vertex of the parabola is going to be when p is equal to halfway in between these two values. Well, we just figured out what those two values are. 0 and m. So the vertex of the upside down parabola, also known as the maximum of this parabola, is going to be at half of m. So what we see there is the fastest rate of growth is going to be equal, or it's going to occur when the population is half of the maximal carrying capacity. That's an important thing to notice. If for the fastest rate of growth, I guess that's the answer to number 3 here. The vertex of the parabola occurs at half the maximal carrying capacity, which means when we look back at this parabola and the height is talking about the rate of growth. So the maximal rate of growth occurs here when the population reaches half of the maximal carrying capacity. That's something important to remember. Fastest rate of growth at half of the maximal carrying capacity. We'll summarize that over here on number 3. Fastest growth at half maximal carrying capacity. Now this next question, number 4, is a little bit harder to understand. If the initial population is less than m, is the initial growth rate positive or negative? Well, what you have to consider is your population can never be negative, right? So again, we're talking about population, so we're only talking about positive populations. Bringing that back to this graph right over here, we're talking about what happens if your population is in between here and here. Now keep in mind, this represents our growth. Our growth in between 0 population and m population, our growth is going to be above the x-axis. Above the x-axis means dp dt is going to be positive. So if we have some sort of population that is above 0 but below the maximal carrying capacity, we are going to have a positive rate of growth. So the way that we say that is, as long as you have under the maximal carrying capacity, you are going to have positive growth. Again, 4 is if the initial population is less than m, is the initial growth rate positive or negative? We'll summarize that as p less than m means that dp dt is positive. It's greater than 0. Next question we have here, number 5, if the initial population is greater than m, is the initial growth rate positive or negative? Well, again, we can't talk about the population being less than 0, but we can go have our population be beyond m, following our rate again, our rate curve here, it looks like that parabola is extending below the x-axis. So if we start out with a population above the maximal carrying capacity, our growth rate is going to be negative. So the way to look at that, again, the maximal carrying capacity is the most items you can have in a population, like the deer in my backyard. Let's say I start off with 5,000 deer in my 1/3 of an acre in my backyard. They're pretty quickly going to have to start dying off in order for me to have enough space to support those deer. So if my population is greater than my maximal carrying capacity, that means that the rate of growth is negative. Looking back here, we're up to number 6. If the initial population equals m, what is the initial growth rate? Well, there we go. Number 6, if p equals m, that means dp dt is equal to, looking up here, k times m minus m. It feels like we already said this before. Look at that. If p equals m, then your rate of growth is equal to 0. So if you're at the maximal carrying capacity, you can just support that number of items in that population. Whatever the items are, whether it's deer, bunnies, bears, whatever. Number 7 asks us, what is the limit as t approaches infinity of p of t? The limit as t approaches infinity of the population. And that's just where the population is settling. If we start with a population less than m, we're going to grow. If we start with a population greater than m, we're going to decay. If we start at a population equals m, we're going to stay at exactly the same amount. So think about that. Population smaller than your maximal carrying capacity, we're going to grow until we reach a growth rate of 0. And that growth rate of 0 happens at m. If we start with a population bigger than our maximal carrying capacity, we're going to decay. And that's going to decay until we get to 0, which occurs when p equals m. So the limit as t approaches infinity of p of t is going to be equal to the maximal carrying capacity. What that says is whatever a population is, the graph is just going to level off at the maximal carrying capacity. And I'll show you what a logistic growth model looks like, the general solution. But before we get there, I do want to, I do want to answer this question. The growth rate of a population P of bears in a newly established wildlife preserve is modeled by the differential equation dp dt is equal to 0.008 p times the quantity of 100 minus p, where t is measured in years. The first question of what is the carrying capacity of bears in this wildlife preserve, you can do this one of two ways. You can look at the general solution. Is that page up? Not the general solution, the differential equation for the logistic growth, and you can see that this logistic growth differential equation matches that pretty clearly, and you can find out what m is just from the structure. But I don't like memorizing stuff, so what I like to do in number A, the carrying capacity occurs when the growth rate is 0. 2 times where I'm going to have a growth rate of 0. Population is 0. Well, that would be, make that 0. I look for anything else that's going to make dp dt equal to 0. So dp dt is equal to 0 when p equals 0, or, looking at this equation, I see if I plug in 100, I'm going to get 100 minus 100. 100 minus 100 is 0. 0 times whatever is going to give me a growth rate of 0, right? So that's when p is equal to 100. So therefore, the maximal carrying capacity is equal to 100. What that means is, in this wildlife preserve or whatever, the most bears that I can have is 100 bears. So the maximal carrying capacity is 100. I guess I should actually put down bears so that I don't. I gotta use units. It's a real world application. What is the bear population when the population is growing its fastest? Okay, I remember back. My maximal carrying capacity is 100. My fastest growth rate is at half of m. So fastest population growth. Fastest growth at half of m, half of 100, which is 50 bears. If I've got 50 bears in my wildlife preserve, that means I have the fastest rate of growth. They're reproducing as fast as possible, and none of them are having to cannibalize to drop the rate. Let's see, what is the rate of change of when the population is growing the fastest? So here, in order to find out the rate of growth, it is asking what is dp dt. So dp dt is going to be equal to, again, we say that the fastest growth rate occurs when we have 50 bears. So we're just going to plug in 50 for p. We'll have 0.008 times 50 times 100 minus 50. And looking at that, well, 100 minus 50 is 50. I don't really know the answer to this one. Might have to use my calculator. Hold on one second, let me get it. Okay, so 0.008 times 50 times 50, 20. It looks like I'm going to have 20 as my growth rate. So this is going to be equal to 20, and I got to make sure that I'm using the correct units. Again, it's dp dt, so dp is measured in bears per dt. I think I know t is measured in years. So it's measured, the fastest growth rate is 20 bears per year. When I have 50 bears in my wildlife preserve, I'm going to be producing 20 bears per year. It's a lot of bears. That scares me. All right. The process through which we find particular solution to the logistic equation is long and complicated and involves partial fraction decomp. If you want to see it, it is actually a fun process. Come see me during office hours. If we have time, I'll show it to you. For the rest of you, you actually have a formula. If you have dp dt is equal to kp times quantity of m minus p, you can have the general solution to that of p is equal to m over 1 plus a e to the negative mkt, where a is a constant determined by an appropriate initial condition, the carrying capacity is m, and the growth constant is k, and they are both positive constants. What I would recommend, maybe commit that to memory. I've never actually seen on the AP test a problem where they ask you to find the particular solution to a logistic growth problem. But if they did, it'd be in your calculator section. So, there's that. So let's see. I think I have a situation here. 10 grizzly bears were introduced to a national park 10 years ago. There are 23 bears in the park at the present time. The park can support maximum of 100 bears. Since I know that I have a maximum of 100 bears, I know that m is equal to 100. I can actually mine this information to find out that my k is 0.001. So looking at this, again, I'm trying to match this general solution that p equals m over 1 plus a e to the negative mkt. Again, that is, give me a pen, p is equal to m over 1 plus a e to the negative mkt, a e to the negative mkt. I can look through this equation and I can find my maximal carrying capacity. Again, however I want to do it, I look for where I have a population growth of 0. That's if I plug in 100 there. And my k is equal to 0.001. I'm going to plug that stuff into my equation right here. So I'm going to have my population is equal to my maximal carrying capacity, 100 over 1 plus a. A is some constant determined using some sort of condition. I don't know that condition yet, so I'm going to leave it as a. E to the negative m 100 k. K was 0.001, 0.001 t. I'm going to simplify that a little bit. 100 times 0.001, I believe, gives me 0.1. 100 over 1 plus a e to the negative 0.1 t. So there I have sufficient information, although I don't have my a. The one thing that I have left to do here is to determine my a. And the only way that I can determine my a is by using this information. 10 years ago, we had 10 grizzly bears. Now we have 23 grizzly bears. We can use either one of those conditions to find my a. Since I'm talking about 10 years ago, I'm going to consider 10 years ago, t equals 0, means the population at that point was 10. Or I could have t is equal to 10 years into the experiment, where the population is equal to 23. Either of those conditions is going to allow me to figure out my a. Which one's going to be easier to use? Obviously, I hope the one with a t equals 0 is going to be easier to use. So I'm going to have my population, my population of 10 is going to be equal to 100 over 1 plus a e to the negative 0.1 times 0. Negative 0.1 times 0 is 0. E to the 0 is equal to 1. So I'm going to have 10 is equal to 100 over 1 plus a times 1. Solving this, I'm going to get, let's see, cross multiply. So I'm going to have 1 plus a is equal to 100 over 10, also known as just 10. So now I get a is equal to 9. And my general solution, or my particular solution, not my general solution, my particular solution is going to be p is equal to 100 over 1 plus 9 e to the negative 0.1 t. There's my particular solution. Woohoo! Now I want to find out, when will the bear population reach 50 or 75 or 100? The best way to do this is to graph this function. So you can see I pulled out my calculator. I'm just going to graph the population function here. Fraction 100 over 1 plus 9 e to the negative 0.1 t. I'm going to graph it. I think really looking at this logically, I know that I have 10 years for this bear population, right? So I'm looking in my window. I want, in 10 years, it was at 23 bears. So I want to go from time 0 to time, I don't know, let's guess 50 or so, like that. My maximal carrying capacity was 100 bears. So I know that my Y max is going to be 100. So looking here, let's see if I can get the whole graph there. Not quite, because I'm not seeing this flattening off over right here. I want to extend my time out a little bit. Let's see what happens when we go out to 100 years. There we go. That looks a lot better. So here, that's what a logistic growth looks like. It's kind of like a sideways S. All logistic growth curves, when you graph the particular solution, are going to look like that. Now, when we see this, we want to find out, when will the bear population equal 50, 75, or 100. Easiest way to do that, 50, 75, 100. And when we graph those, where's the function going to equal 50? Right here. Find that, second trace, intersect, blue, red, enter. There we go. Almost 22 years there. Find the next one, intersect, blue, wait a second, intersect, blue, black, enter. I can see that's going to happen at almost 33 years. Now, when is the population going to reach 100 bears? It's never going to quite reach 100 bears, but it's going to get pretty darn close. We know that we can't have like half of a bear, because that's illegal. We're not allowed to cut bears in half. If we trace along this, we're just looking for where would we round up to 100 bears. It looks like about 75 years we would have 100 bears right there. So that's pretty much everything from this section, and consequently everything from this chapter. Now there's a couple, like an example of an AP problem that I have right about here. The function n satisfies the logistic differential equation. dn dt is equal to n over 10 times the quantity of 1 minus n over 850, where n of 0 is equal to 105, which the following statements is false. You can try to start eliminating stuff like the limit as t approaches infinity of n of t is equal to 850. Well, we know that this function is going to level out at its maximal carrying capacity. If I plug in 850 up here, I would have 1 minus 850 over 850. I would have dn dt is equal to 0. That's how I know that 850 is my maximal carrying capacity. A is true. dn dt has a maximum value when n equals 105. Let's see, maximum. No, that's not true. This is not true because the maximum value of the rate of growth is at half of 850, which is 425. B is wrong. Looking a little bit further, I know that since I have the maximum of dn dt, the second derivative would have to be equal to 0, so that is true. And when n is greater than 425, dn dt is greater than 0, and second derivative, d2n dt2 is less than 0. So again, we're talking about the growth is positive, so we have positive growth, but here at that second part of the logistic growth curve, we have a concave down, so that one is false as well. Whew, this was a fun day. You will be able to do the entire homework without doing a single bit of calculus. I will point out that I didn't really do too much calculus in this video. Sorry for it being so long. Goodbye.